Okay, let's start. Today we will do the most important part is binomial theorem, and this section is actually not too long, not too short, but requires us to learn some new tools. The first tool that we will learn is factorial. The factorial notation is exclamation mark. This one here. Okay, for a natural number n factorial means n times 1 less than that times 2 less than that, and all the way down to 2 times 1. So 4 factorial means you start from 4 and then you multiply all the way down to 1. 7 factorial means you start from 7 and then you multiply all the way down to 1. Okay, now let me ask you to use your calculator to show that you know how to compute this. Let me ask you to compute 4 factorial first. 4 factorial, using this, you punch 4 and then PRB. The PRB button is here. That's the PRB button. And then you choose exclamation and then enter. After that, you will see 4 factorial on your screen. Then you press enter. You should get 24. Okay, you should get 24. Now please confirm that you get the same thing. I have, my calculator is TI-84. So the way to press that will be different. And 7 factorial, I get 5040. Can you confirm? Otherwise, you just use your calculator. 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay. Can I go on? I rather you try that first. If you use TI-36, I believe that will be the same way of punching, even though the PRB button may be different place. But it must be somewhere there. Is it okay? Now, let me go on. The second tools to know is combination. Definition for natural numbers R, N and R, natural numbers. Actually, I should not say natural numbers, whole numbers. For whole number N and R, parentheses, N on the top, R at the bottom, but no lines. It's not a fraction, no lines, okay? No fraction, not a fraction. This notation also denoted as, our textbook also known as C n comma K. Our calculator write it as N C K, where the N, I'm sorry, not K, R, where the N and the R are subscript on the last notation. That means N factorial over R factorial N minus R factorial. Now, this may seems to be complicated, but actually not really. And even when it gets complicated, when the number gets larger, we can use calculator. Okay, let's see what it means first. For example, because if the number is small, we tend to use, I tend to just use, do it by hand. Okay, let's say I have 7 combination 4. Okay, if you use this notation, the 7 and 4 are subscript. Okay, smaller and lower. Our textbook will use this notation. 7 on the top, 4 at the bottom, but again, it's not a fraction. Okay, don't put a line here. No, don't put a line there. Okay, now this means, according to our definition, is 7 factorial over 4 factorial, 3 factorial. No, but if we spell this out, 7 factorial means 7 times 6 times 5 times 4 times 3 times 2 times 1 over 4 factorial times 3 factorial. Now, the reason I teach you how to do it by hand, because when the number is small, it's actually easier to compute manually compared to if you take some time grabbing your calculator. I can do any number combination too mentally. Yeah. So 7 combination 3, for example, I may need to think a little bit, but less than 10 seconds. Okay, because I get used to it. And if you are actually going to probability, which is my field, probability is one big field from math, then you need to deal with a lot of combinations. One of the earliest distribution in probability statistic that you have to memorize is binomial distribution that comes from binomial theorem. Okay, now let's come back here. 7 factorial, 7 combination 4. Sometimes I say 7 choose 4. Means 7 factorial on the top. At the bottom, we have 4 factorial, 3 factorial. You will see that the sum of these two numbers here will be equals to this number. Okay, now then, before we really compute it, notice that the 3 factorial cancels. So when we say 7 combination 4, basically means you start from 7, and then have 4 factors down, like 7, 6, 5, 4. And on the denominator, you have 4, 3, 2, 1. From there, you can compute it. Okay? From there, we can compute it. That will be what? So 4 cancel the 4, 6. So that's equals to 35. Okay. Let's do more. Let's say 10 combination 2, which is parenthesis 10 on the top, at the bottom 2. That will be 10 times 9. Remember, you start from 10, 2 factors. At the bottom, you start from 2, going down to 1. That's it. That's 45. Yeah, if the number is small, actually, you can just do it by manually. Okay, let's say 12 combination 3. That means 12 times 11 times 10 over 3, 2, 1. 6 goes into 12 2 times. So this is 220. Like that. Okay. Now, how to use these combinations, actually we'll see more in probability, to be more precise, statistic. But for now, we will use this actually quite far later on in another half an hour. Okay. If you want to use calculator, The idea is you will punch, let's say 10 combination 2, right? Then you will punch the 10 first, and then NCR, and then the 2, and then enter. Now the thing is where you find your NCR. You find your NCR at PRB NCR. Okay, now try 10 PRB NCR, enter, and then 2, and then enter. You should get 45. Try it, please. Let me use my TI-84 to show you. So my TI-84, let me make it a bit larger. Okay, so let's say I want to do 10 combination 2, 10. And then I go to, for my calculator, I go to math, but basically I go to this PRB, and then NCR, 2, enter. Now for you, you may need to press enter after you press NCR. You try it, you figure out how to do that. That's not a question you will ask me during the test. Okay, that's not a question you should know this already by that time. Is it okay? Yes, no, no, yes. Okay, now let's try one more. How about if I have, try this one, 12 combination 3. Do you really get 220? Okay, I assume you get it. Okay, now let me go on. The real binomial theorem. Okay, idea for binomial theorem. What we are going to do with this. Binomial theorem is actually one of the very important building block that you need to know before you go to pre-calculus, before you go to calculus. Now, some instructors don't realize this, okay, but those instructors who realize that actually emphasize this and insist to teach this before, basically on the last week of the class or the second from last week from the class, like I do right now. Okay, here's the idea. Okay, we know that x plus y squared is x squared plus 2xy plus y squared. Okay. And for example, x plus y cubed, oh, I don't know that one, but I can compute that myself, x plus y times x plus y squared. Is that right? And this is x plus y times, according to what we have above, x plus y squared is x squared plus 2xy plus y squared. And then this will be x cubed plus 2x squared y plus xy squared plus x squared y plus 2xy squared plus y cubed. And this is x cubed plus 3x squared y plus 3xy squared plus y cubed. Now, the purpose of binomial theorem is to find the expansion of x plus y to the power of n, where n is a natural number. Okay, we want to find the expansion. So this section here, the binomial theorem, sometimes also named the binomial expansion. No, not exponential, expansion. You expand it. Expand. The root word to expand. Okay, to spread it, to multiply it out. Okay, that is expansion. Is it with A or E? Let me see. I think it's with an A, not with E. Yeah, expansion with A. Now, for now, we have seen some pattern. Well, let's do one more. Let's do one more. How about x plus y to the 4? X plus y to the 4 is x plus y times x plus y being cubed. From what we had earlier, x plus y cubed is x cubed plus 3x squared y plus 3xy squared plus y cubed. That gives us x to the 4th plus 3x cubed y plus 3x squared y squared plus xy cubed. And then plus x cubed y plus 3x squared y squared plus 3xy cubed plus y to the 4th. And we get x to the 4th plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the 4th. Now, what I want you to observe is the following. First, x plus y to the n has n plus 1 terms. So if the exponent is 2, then you will have 3 terms. If the exponent is 3, then you'll have 4 terms. You see that? If the exponent is 4, then you will have 5 terms. Is it okay? Second, the expansion starts with x to the n. And then the next term, you will see the exponent of x reduced by 1. but the exponent of y suddenly increased by 1. Now the total exponent is still n. Okay, take a look on the exponent here. You see degree of 4, but this is still degree of 4, 3 plus 1, degree of 4, degree of 4, degree of 4. You see that? Think of it this way. The degree of the x term, if we have x plus y to the n, then the degree, you start from x to the n, and then x to the n decreases while the y increases from y to the 0 to y to the n. The x decreases from x to the n to x to the 0. So we can say it this way. If I go to another example here, let's say if I have x plus y to the 6, then I know for sure that will be x to the 6 plus something x to the 5th y. You see, the exponent for x reduced by 1, but the y now shows up, y to the 1, plus something x to the 4th y squared. You see the exponents still add up to 6, plus something x cubed y cubed, plus something x squared y to the 4th, plus something x y to the 5th, plus y to the 6th. Can you follow me? Okay, now the third part is the coefficients of the terms will be obtained by two methods. First one, Pascal triangle. And second one by combination. So once you see the pattern for the terms, how the x and y actually decreasing and increasing, then we will learn to find how to find the coefficients. Okay, now two methods to find coefficients. Two methods to find coefficients. The coefficients of binomial expansion. The first one is Pascal triangle. Pascal triangle is built this way. You start with 1 and then 1, 1. The next row, you start from 1 on the outside. In the middle, you add these 2. So you can see it this way, like this. And then the next row, 1 by itself, this is 3, this is 3, 1. 1, 4, 6, 4, 1. Now notice that this 1 to 1 is the coefficients of x plus y squared equals to 1 x squared plus 2 xy plus 1 y squared. Do you see that? And this row, for example, 14641 is this one here. You see that? Those are the coefficients. Okay, so let me write it down here. That represent x plus y to the fourth. For the terms, that will be x to the fourth plus x cubed y plus x squared y squared plus xy cubed plus y to the fourth with coefficients invisible 1 and then 4, 6, 4, 1. Now, the thing is, this Pascal triangle, you can actually grow it really, really big. Okay, you can grow it to 20 level, 20 layers, 30 layers, and on. But usually we use this, used for small n. And of course, the phrase small n depends on, it's like it's subjective, person to person. Okay, but don't get me wrong, this Pascal triangle is true even if you extend it to 100 layers. Now the thing is, if you notice, for me to get this layer here, I need to work it out. Okay, so for me to have, let's say, 30 layers, I need to work it out all the way to 30, not just like suddenly to the 30th layers. No, I have to work it out. I need to grow this triangle. Okay, which make this method is not quite efficient if the n is large. Okay, now notice in the on the top here we have the expansion for x plus y to the 6, right? We are missing the coefficients, right? Now notice that the first and the last coefficient always 1. The first and the last coefficient always 1. You see that? Okay, in fact, we can say more, that the second coefficient always equals to the exponent. So we can say for sure here must be the same to this. It must be 6. And by symmetry, the second from the last also equals to 6, which is the exponent of x plus y to the 6. Okay, but let's find the rest. What are these numbers? We know that these two numbers must be the same, right? Okay. Now, by extending this is 1, 5, 10, 10, 5, 1, but this is to the power of 5, and 1, 6, 15, 20, 15, 6, 1. So this must be 15, 20, 15. Is it okay? Now let's do one more example. Let's do one more example. Suppose I want to do the extension of x plus y to the 7th. Then I know it must be x to the 7 plus something x to the 6y plus something x to the 5th y squared plus something x to the 4th y cubed plus something x cubed y to the 4th plus something x squared y to the 5th plus something xy to the 6th plus y to the 7th. And as for the coefficients, let me go one more layer here. So I get 1, 7, 21, 35, 35, 21, 7, 1. Okay, so for the variables, we know that the first variable will start from n degree and going down. The second variable will start from 0 degree and then going up. And then the coefficients, you can get it from Pascal triangle. Now, I won't teach you the second method yet, but let me strengthen your foundation first, how to use this. Let me strengthen your foundation first, how to use this. Suppose, for example, and this is what I barely teaching this last night with my Calculus 2 class on how to use the following, of course, not the simple one, but how to do the following extension. Okay, suppose I have 3x squared plus 4y cubed to the power of 3. How do we extend this? Solution. I will start with a plus b to the power of 3. What is the parent? I want to get the parent, and then later on I substitute the a and the b. This is a cubed plus 3a squared b plus 3ab squared plus b cubed. How do you get that, Thomas? Well, the exponents, a cube going down, going down, going down, and the exponent for b start from b to the 0, b to the 0, b to the 1, b squared, b cubed. And then the third component, the coefficients, come from 1331 in the Pascal triangle. 1, 3, 3. Okay, what this has to do with the question, Thomas? Well, basically, now you can substitute your a by 3x squared and your b by 4y cubed. So this is 3x squared being cubed plus 3x a squared b plus 3a b squared plus b cubed. Do you see that? I do substitution now. This is my a. And this is my b. I hope you see that now. Okay, I hope you see that. Yeah, the nice thing about teaching online, the one other thing I like about teaching online is I have basically 5 different colors for my pen, and I have 4 different colors of highlight plus some small highlights, which I don't have when I teach in class. In class, at most I have 2 markers, black and blue, or 4 if I'm lucky, black, blue, red, green. You know, but here I have 5 at least for markers and then some highlights. You know, so I can't really do this when I teach in class. Well, anyway, now of course I'm not done yet, but everything after this just simplification. This will be 27x to the 6 plus 3 times 9x to the 4th times 4y cubed plus 3 times 3x squared times 16y to the 6th plus 64y to the 9th. Make it even nicer, 27x to the 6 plus 108 x to the 4th y cubed plus 16 times 9. I think it's 144 x squared y to the 6 plus 64 y to the 9th. Do you see that? Okay, so first I get the pattern first. Okay, something cubed. So let me get a plus b cubed. What's the pattern? And then after that, I do substitution. Okay, after that we do substitution. So let's try, for example, number 25 in our textbook. Number 25, we have 3t minus 5s to the 4th. How do I extend that? Let me use the dummy a plus b to the power of 4. I think it's 14641, right? So a to the 4th plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4th. Now we substitute the a to be 3t and the b to be negative 5s. So this is my a, this is my b. So I get 3t a to the 4th plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4th. This is 81t to the 4th plus 4 times 3 times negative 5 t cubed s plus 6 times 9 times 25 t squared s squared plus 4 times 3 times negative 125 t s cubed plus 625 s to the 4th. But basically everything after this is algebra. Or I can even say this arithmetic. Negative 60 t cubed s plus 150 times 9 is what? 135. So t squared s squared plus 12, actually not plus, it will be minus, times 125 is 1500. You see what I mean? Of course, you can always go large. You can always go large, but when the n is a lot larger, then it may not be efficient to use Pascal triangle anymore. Now, let me do one more, number 27. Let me do one more, number 27. Number 27 from our textbook is 1/3 x plus y squared to the power of 5. Let me use dummy variable, a plus b to the 5th. That's a to the 5th plus 5a to the 4th b plus 1, 4, 6. So that will be 10a cubed b squared and then 10a squared b cubed 1, so 1, 4, 6, 4, 1. So 1, 5, 10, 10, 5, 1. Let me see, did I make any miscomputation? Isn't we have to 3 to the 3 in the second term? Oh yeah, that's right. That should be 27 here, huh? So it should be 27 there. So times 9 is 540, like this. Am I good now? Yeah, multiply by 9, right? Thank you. 1, 5, 10, 10, 5, 1. Okay, now then I switch back to 1/3 x plus y squared as my a plus b. So this will be 1/3 x to the 5th, that's my a to the 5th, plus 5 times a to the 4th b, plus 10 times a cubed b squared, plus 10 times a squared b cubed, plus 5 a b to the 4th, plus b to the 5th. Now this will be 1/3 to the 5th x to the 5th plus 5/3 to the 4th is 81, x to the 4th y squared, plus 10/27 x cubed y to the 4th, plus 10/9 x squared y to the 6th, plus 5/3 x y to the 8th, plus y to the 10th. 3 to the 5th is 241, I believe. 243. 81 times 3, right? Do you get it now? Okay, now let's go large. Let's go large. The second method is by combinations. You will see that when we have x plus y to the n, that is actually equals to, the coefficient is actually given by n combination 0 x to the n plus n combination 1 x to the n minus 1 y, n combination 2 x to the n minus 2 y squared, all the way to n combination n minus 1 x y to the n minus 1, n combination n of y to the n. Now you see that the coefficients, basically, the coefficient of the terms is given by n combinations, the exponent of y. Okay, so if I expand this a plus b to the fifth using combinations, a plus b to the fifth, this is the same to 5 combination 0, a to the fifth, plus 5 combination 1, a to the fourth, b. 5 combination 2, a cubed, b squared. Notice that the sum of the exponents still 5, right? Okay. So 5 combination 3, a squared, b cubed. 5 combination 4, a, b to the fourth. 5 combination 5, b to the fifth. And when you compute that, you will get this is 1a to the fifth, 5a to the fourth b, 10a cubed b squared, 10a squared b cubed, 5ab to the fourth, b, 1b to the fifth. So the same coefficients there. Now, good informations to know that n combination 0 is always equals to n combination n, which is 1. Okay. If you are in my probability or statistic class, I will explain even more why this is true logically. Now, for you, at least from the definition of n combination 0, this is n factorial over 0 factorial, n minus 0 factorial. That's n factorial over 0 factorial, n factorial. N factorial cancels, right? And 0 factorial is defined to be 1. Now, n combination n is n factorial over n factorial, n minus n factorial, which is n factorial over n factorial 0 factorial, which is the same to this, right? Do you notice that? It's the same. Also, n combination 1 is equal to n. By symmetry, this is the same to n combination n minus 1. See, the number you have here, that's the second from the first term, right? Second from the front is the same to second from the last coefficient. In other words, as long as the r, the number at the bottom, add up to n, which is the number on the top, then they must be equal. Okay, so the third term from the front is the same to the third term from the back. Okay, those are nice things to know, but if you don't know that, you're totally fine. Okay, that's not something you need to know from this topic. But that tells us important things on how to expand it even larger. Suppose I want to expand this. Suppose I want to expand, let's do this one first. A plus b to the power of 10. Ooh, this is large. This is large. How many terms? There should be 11 terms, right? There should be 11 terms. So a to the 10 plus 10a to the 9b. The coefficient of the second term always n. And then this guy here, I don't know anymore. This is 10 combination 2, a to the 8th b squared, plus 10 combination 3, a to the 7th b cubed. You see that the number at the bottom here always the same to the exponent of the second variable. Okay. Now, let's do it one time, like a big one, and we do a full extension, and we don't do this anymore. I just write them down. I don't compute anything yet. I don't compute anything yet. At least I get the pattern and the coefficients. Now, put in the pattern. So this is a to the 10 plus 10 a to the 9b. 10 choose 2 is 5 times 45. 10 choose 3, 10, 9, 8, 3, 2, 1. This is 3, this is 4, that's 120. $210. So I don't even know what is this anymore. It's 10 combination. Let me write it properly. I'm so lazy to use my calculator. 5, 4, 3, 2, 1. 3, 2 cancels the 6. Cancel 2 here. This is 2 here. So 36 times 7, 42, 4, 252. And then from there we get the symmetry, right? 10 combination 6 is the same to 10 combination 4. That's 210. And then 120 a cubed b to the 7th plus 45 a squared b to the 8th plus 10 a b to the 9th plus b to the 10th. You know what? Let me make sure it's 252. 10 choose 10. 10 choose 5. Yeah, that's right. That's 252. That's the expansion. Now let's see number 35. Number 35. Okay, find the first 3 terms. Find the first 3 terms of 3c to the 2/5 plus c to the 4/5 to the 25th. The first 3 terms. Okay, let's do the template first. For example, I'm sorry, not solution. Solution. I will do the template first. A plus b to the power of 25. That will be a to the 25th plus 25a to the 4th b plus 25 choose 2. That's 12 times. That's 300. Maybe I write it down. Yeah, that's 25 combination 2 of a to the 23rd b squared. But we just need the first 3 terms, right? Okay, so this is a to the 25th plus 25 a to the 24b plus 25 combination 2, 25 times 12, that's 300 a to the 23rd b squared. Okay, now substitute the a by 3c to the 2/5, substitute the b by c to the 4/5. That will be 3c to the 2/5 to the power of 25 plus 25, 3c to the 2/5 b, which is c to the 4/5. This is 24 here, plus 300, 3c to the 2/5 to the 23, plus times c to the 4/5 square. This is 3 to the 25th times c to the 10th, right? 2/5 times 25. Okay, plus 25 times 3 to the 24, c to the 48 over 5, c to the 4/5, plus 300 times 3 to the 23rd, c to the 46 over 5, c to the 8 over 5. Go on further, let me just leave it like this. 3 to the 25th, c to the 10th, plus 25 times 3 to the 24th, c to the, what's that, 52 over 5? Plus 300 times 3 to the 23, c to the 54 over 5. And the reason I told you that this is important for your calculus, especially your calculus 1, chapter 2, or chapter 3, as I know supposed to be chapter 2, but maybe chapter 3. Okay, somewhere in future you have this. This is an example from me. Find different quotient of the function for fx equals to, let's say, x to the 5th. Do you remember this question in your test 1? I can ask you this. I don't have that plan, but I have all the right to ask you this question at this point. Okay, now you will encounter this type of question in your calculus 1, very likely in chapter 2, maybe chapter 3. Okay, now, but how to do this? Solution. Now the thing is, difference quotient of function f is f of x plus h minus fx over h. I wonder if you remember this. Long time no see, huh? Okay, so the first thing you need to find is what is f of x plus h. That is x plus h to the 5th, right? Which is x to the 5th plus 5x to the 4h plus 1, 5, 10, 10, 5, 1. Yeah, I'm referring to this expansion here. 1, 5, 10, 10, 5, 1. Okay, so the difference quotient will be x to the 5th plus 5x to the 4h plus 10x cubed h squared plus 10x squared h cubed plus 5x h to the 4th plus h to the 5th minus x to the 5th, right? Minus the fx. This guy, this guy. You see that? Okay. All over, you know what? The second part, let me use different color. All over h. But you see on the numerator, the x to the 5th cancels. So I have 5x to the 4h plus 10x squared, x cubed, h squared plus 10x squared, h cubed plus 5x h to the 4th plus h to the 5th all over h. But remember, we cannot stop here because if I substitute the h by 0, I will get 0 over 0. Okay, if you have 0 over 0, then you cannot stop there. You need to go on further. And one of the one thing we can do is factor the h. So the difference quotient of x to the 5th is 5x to the 4th plus 10x cubed h plus 10x squared h squared plus 5x h cubed plus x to the 4th. This becomes the very foundation of derivative of a polynomial in calculus 1. Okay, so definition, just give you a heads up, like what is if fx equals to x to the 5th, then f prime x is equals to limit h going to 0 of fx plus h minus fx over h. Now, we have done this part. We have done this part. We have done this part. That's the difference quotient. Your calculus will send the h become 0. So you will see this cancel, 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 cancel. When h going to 0, then the derivative of x to the 5th is 5x to the 4th, like that. Okay, so your calculus later on will work with the limit condition only, which is not supposed to be too hard at that level. Okay, the hard part will be the pre-calculus part, the difference quotient. Now notice that our textbook does not emphasize difference quotient that much. I do. Why? Because when you go to calculus, when you learn a chapter of derivative, it's not only a section, it's actually a chapter on derivative and how to use them, the implication, so on and so forth. That's actually from difference quotient. Okay. Now, of course, then once you get to calculus, you will learn more or more shortcuts. Okay. But I believe you're supposed to learn the foundation first there. So maybe the first day you learn derivative, you do it this way, and then the next day your teacher will teach you shortcut. Okay, let's do more. Let's do more. Let's say I do number 39. See, once the n gets larger, they usually don't ask you to write down all of them. They usually don't ask you to write down all of them. They just ask you the specific term. Like this one here, they ask you the 6th term of the expansion. What is the 6th term of this expansion? Let's see. If I have a plus b to the power of 7, then the 6th term must be a squared b to the 5th. Think about this. Because the first term will be a to the 7th. The second term will be a to the 6b. The exponent of b is 1, but this is the second term. The third term, you have exponent b squared, right? That's the third term. That's the third term. This is the second term. So the 6th term must have b to the 5th. Agree? Now, how about the coefficient? The coefficient will be 7 combination 5. How do you know 7 combination 5? 7 for the exponent of the n, 5 for the exponent of b. Now change it back. 3 over c plus c squared over 4 to the 7th will be 7 choose 5, that's 7 times 3, 21. The a is c 3 over c squared. And the b is c squared over 4 to the 5th. So the 6th term is given by 21 times 9 over c squared times c to the 10 over 1024. That is 189 over 1024 c to the 8th. Instead of multiplying them, foiling them 6 times, and then see what is the 6th term, if you don't make mistake with your fractions, right? Okay, now I would like you to try number 41 with your break. Number 41, 1/3 u plus 4phi to the 8th. We want the 7th term. Also, number 45, why not? So let me break it up here. Number 45. 2y plus x squared to the 8th. We want the term that contains x to the 10th. Okay. 3 minutes for each plus your break. We come back at 9:26. Okay, let's start. Our SI leader has an announcement. Go ahead, Malaki.
Hi. Yeah, I just wanted to let you guys know that I'm going to be having my final review session on Saturday, June 5th. Let me get the exact time. Sorry about the noise. So I will have my my final review session on Saturday, June 5th from 10 a.m. to 2 p.m. So this is going to be a 4-hour just comprehensive review of everything from the class. We're going to use an old final exam that Thomas gave in the past. And we're going to just go one by one through the questions. So if you need a review before the final, come to that. I'm going to send more information out in an email after class today. So look out for that. All right. I hope to see you guys at the final review.
Thank you very much. Okay, let's continue here. Number 41. Let's see. Solution. If I had a plus b to the 8th, then the 7th term will be am I at the right sharing? Okay. The 7th term will be b to the 6th, right? So the a will be squared and it will be a combination 6. So the 7th term will be 8 combination 6, that's 8 combination 2, 4 times 7, 28. 28a squared b to the 6. Now then, if I get to 1/3 u plus 4 phi to the 8th, then the 7th term will be 28 1/3 u squared 4 phi to the 8, to the 6. So that will be 28 times 1/9. 4 to the 6 is, let me just make it 4 to the 6. U squared phi to the 6. Number 41, yeah. So this is the number. Okay, just use your calculator. So something over 9 u squared phi to the 6, and use your calculator for that. Okay, number 45. The terms that contains x to the 10th. To have x to the 10th, there must be x squared to the 5th. Is it right? Okay, so we kind of like build this back. If it is x squared to the 5th, then it must be 2y cubed. Is it right? And this must be 8 combination 5. You see what I mean? So 8 combination 5, 8 choose 3, 56 times 8y cubed x to the 10th. So that's 448 x to the 10th y cubed. Easy, right? Not too hard, but it's like you have to notice the pattern. You need to notice the pattern. Okay, now suggested homework from here. Suggested homework from here. I would like you to be able to do, especially from this 9.5, especially from number 19 to number 47. Just do the odd ones. Okay, but if you have little time, train your calculator skill from number 1 to number 17. But do the 19 to 47 first. The last question is the 6 terms. Yes, you can say it that way. You can say it's the 6th term. Yeah, you can say it's the 6th term for the last one. Okay, let's continue. I now go back to 9.1. 9.1 and 9.5 actually almost not related at all. Almost not related at all. What is 9.1? 9.1 is on sequence and series. And series. I think they call that summation notation. What we learn in this 9.1, mostly definition and little computation. It's supposed to be easy. 9.1 supposed to be on the easy side. Okay, but we start recognizing some pattern. Definition, what is a sequence? A sequence is a list of numbers in certain order. Now, we usually denote it by a sub 1, a sub 2, a sub 3, and on to represent the first term, the second term, the third term, and on. Okay, now there are, let's say this example here. Suppose, for example, we have this sequence 3, 7, 11, 15, 19, and on. Let's say we have that sequence. Now then the first term is 3, the second term is 7, the third term is 11, the fourth term is 15, the fifth term is 19. And you see the ellipsis there, it means it goes indefinitely far. That creates infinite sequence. Now, our textbook correctly define it slightly different way, but actually the same meaning. Okay, they define it as this: a sequence is a function with positive integer domain. So we can say that our a sub n, you can think of that as fn. You can think of that as fn, where n is a natural number. Okay, now that's because one of the method to write a sequence is by using functional or formula. Okay, there are 3 methods to express a sequence. The first one, the one we have above by listing. That's the one we have above. For example, that's 3, 7, 11, 15, 19, and on. The second method by formula or function. For example, a sub n equals to 4n minus 1. So I give the formula a sub n is 4n minus 1. So the first term will be 4 times 1 minus 1. Now you see why we call that functional notation? Because you basically replace the n by 1, by 2, 3, 4, and on. This is equals to 3. A sub 2 is 4 times 2 minus 1, that's 7. A sub 3 is 4 times 3 minus 1, that's 11, and on. Now, this functional notation may also written as, they may also write it as bracket. I'm sorry, I should call that braces. Braces 4n minus 1. Okay, now we call that formula, but in set notation. And the third method is called recursive method. For example, we say, oh, a sub 1 is 3. And the next term is the previous term. The next term is the current term plus 4. So if you build that using this, we see that the first term is 3. The second term is the first term plus 4. The third term is the second term plus 4. The fourth term is the third term plus 4, and so on and so forth. Okay, now these are 3 different methods to compute or to express a sequence. Now, for the first couple questions in our textbook, what we need to do only to list from formula or from recursive sequence. Okay, so for example, if we take a look on number 3 in our textbook, it says find the first 4 terms. Find the first 4 terms of and the eighth. So for number 3, we have this sequence here, 3n minus 2 over n squared plus 1. So what is the first 4 terms? What is A1, A2, A3, A4? And the 8th term, A8. You see? So I plug in n equals to 1 here. So that's 3 minus 2 over 1 plus 1. That's 1/2. When n equals to 2, that will be 6 minus 2 over 4 plus 1. That's 4/5. When n equals to 3, 9 minus 2 over 9 plus 1. That is 7/10. A4, that's 12 minus 2 over 16 plus 1. That's 10 over 17. And the 8th term will be 24 minus 2 over 64 plus 1. 22 over 65. It's that simple. It is that simple. It is that simple. Okay, let me ask you to try number 13. Please don't think too hard. Okay, please don't think too hard. 2 to the n over n squared plus 2. Find the first, second, third, fourth term. And the 8th term. You know what? Try number 9 also. Number 9. Yeah, you will see what we call alternating sequence in number 9. The first term, the second term, the third term, the fourth term, the 8th term. Okay, try these two questions. I give you 5 minutes. Okay, let's start. This is 2 over 1 plus 2. That's 2/3. This is 4 over 4 plus 2. That's 4 over 6. That's 2/3 also, huh? And then this is 2 to the third. It's 8 over 9 plus 2. That's 8 over 11. The fourth term, 16 over 16 plus 2. That's 16 over 18. That's 8 over 9. And then the 8th term, that's 2 to the 8th over is 64 plus 2. What's that? 256 over 66. I think I can reduce by 2. 128 over 33. Okay, this one here, I hope you see that the sign alternates. In this case, it will be positive 1 plus 7 over 2 times 1, or let me just use 2 instead. So that's equals to 4, and then negative 9 over 4, and then positive 10 over 6, that's 5 over 3. And then negative 11 over 8, and the 8th term will be negative 15 over 16. I think that's easy enough, right? I hope so. I hope so. It's just plug in numbers. It's just, suppose I give you a function, find out what is f1, f2, f3, f4, f8, right? Okay, I hope you don't find it to be hard. Now, next, what happens if we have recursive? Let's say, for example, number 23, the easy one first. We'll get the first 5 terms. So the first term is -3. The next term is the current term squared. Okay, solution. So the first term is given to us, that's -3. The second term, that's 1 plus 1, right? The second term is the first term squared. The third term is the second term squared. The fourth term is the third term squared. 6, 4, 6, 5, 6, 1. Let me use my calculator. Oh yeah, that's right. Okay, and then the fifth term, oh man, this is big. The fifth term is the fourth term squared. That suddenly becomes a very big number. That's 4, 3, 0, 4, 6, 7, 2, 1. Our textbook is a bit, it's actually cheating. They write it as 3 squared, and this is 3 to the fourth. The 3 squared being squared, it's like 3 to the fourth. Now, if you see the number actually growing fast, will grow fast, it's okay for you to do it this way. So instead of writing the actual number, you give the exponent. You write it in exponent form. Okay, number 27. The first term is 2. The next term is the current term to the power of that k. So what is the first 5 terms? The first term is 2, that's given. The second term is the first term to the 1. The third term is the second term squared. The fourth term is the third term cube. Let me just make it like this. Of course, you can compute that too. This is 4, this is 64, right? And then the fifth term will be the fourth term to the 4. Okay, and then use your own calculator. What's that? We still have a recursive sequence, like for example, number, let's see number 31. At first, you may get confused with the notation, but it's actually still that easy. The first term is 4. The second term is -2. Now, the next term, k plus second, is the current term times the previous term. So the first term is 4. The second term is -2. Now, the third term is the second term times the first term. Take a look. When we say a sub 3, that's a sub 1 plus 2, right? So the k is 1. So that's like a sub 1 plus 1, a sub 1. That's a sub 2, a sub 1, like that. You see what I mean? So this will be -2 times 4, that's -8. Now the fourth term is a sub 3, a sub 2. That's -8 times -2, that's +16. The fifth term is the fourth term times the third term. 16 times negative 8. What's that? That's 120, negative 128. Oh, that's what those means. Okay. Which I hope not too hard for you. Okay, I hope it's not too hard. It's just plugging numbers, really. Just plugging numbers. If you find this section to be hard, you must be thinking way too hard. Next, summation notation. Summation notation. This notation here means the sum of. Okay, now that summation notation should be written as a capital block M that you turn 90 degrees counterclockwise. Okay, so it becomes like this. This is how you write it. This is how you write it. Not like this, not like this, not like this. No, not like that. Okay, not E either. No, it's not. No, this is the correct one. Okay, that's a Greek letter for sigma. In math, this letter, this notation means the sum of, the summation of. Okay, so if we have this notation, the summation of a sub n equals to, let's say, 3, 5. If you see this notation, this means you start from 3 the counter, the index is starting from 3 up to the number on the top, in this case is 5. That's what it means. Now where this part here is what we learned earlier, the sequence. Okay, that's what it means. That's what it means. So let's do simple stuff. Let's do simple stuff. Suppose I look at number 39. Number 39. The summation for k equals to 1 up to 4 for k squared minus 5. So we start from when k equals to 1. 1 squared minus 5 plus k equals to 2 plus k equals to 3 plus k equals to 4, and we stop when k equals to 4. Just like that. Everything else after this is computing. Can you follow me? Now, if you don't see this as simple, I don't know how to make it even simpler. It's just notation, okay? But you need to get used to it though, that's the thing. Okay, you need to get used to it. Again, this is the sequence, right? Where the sequence starts from k equals to 1 to k equals to 4. Okay, that's what it means. Now, everything after this is computation. This is 1 minus 5, that's negative 4. 4 minus 5, that's negative 1. 9 minus 5, that's 4. 9 minus 5, 16 minus 5, that's 11. So that's equals to 10. Is it okay? Now let me make you work on something. They make you work on something. Just notation. This is just notation. So number 37, I think that's quite easy. The summation k equals to 1 to 5 of 2k minus 7. And then how about number 43? I think number 43 requires you to know your fraction, of course, but you should have known that. The summation from k equals to 3 to 6 for k minus 5 over k minus 1. Okay, let me give you 3 or 4 minutes for this. So this is when k equals to 1 plus when k equals to 2, when k equals to 3, when k equals to 4, when k equals to 5. That's -5 plus -3 plus -1 plus 1 plus 3. Oh, that's -5. Not too bad, huh? For number 43, we start from k equals to 3, right? So 3 minus 5 over 3 minus 1 plus 4 minus 5 over 4 minus 1 plus 5 minus 5 over 5 minus 1 plus 6 minus 5 over 6 minus 1. That will be -2 over 2. That's -1. This is -1 over 3. This is plus 0 plus 1. So that's -1/3. Now I want you to notice something, that the number of terms is equals to the number on the top minus the number at the bottom plus 1. Oh, thank you. The last one here is incorrect. So 1 over 5 here. So what is this? This is -4/3 plus 1/5, -20 plus 3 over 15. That's -17 over 15. Okay, now, by the way, going back, the number of terms is the number on the top minus the number at the bottom plus 1. Well, because when you subtract 5 minus 1, that's the number of terms after this first term. Okay, now you see here, 6 minus 3 is 3, but you see we have 4 terms instead of only 3 terms. Now that's 6 minus 3, 3 terms are the number of terms after term number 3. This is term number 3. And you have 3 terms after that. Okay, now why this information is important? Because later on you will see some sneaky, cheesy questions like number 49. Number 49, the summation from k equals to 253 to 571 of 1/3. Now you see that when k equals to 53, it's 1/3. There's no index there, so plus 1/3, plus 1/3, plus 1/3 all the way. Now this is for k equals to 253. k equals to 254 all the way to k equals to 571. But that's basically then means how many terms times 1/3. You see that? (571) minus 253 plus 1 divided. Oh, you know what? That's good enough. This is 319 over 3. Okay, because that's constant term. That's a constant term. Okay, now your suggested homework from this section, 9.1 will be from number 1 to number 13, number 21 to number 51. Do the odd ones. Now, even though seems to be a lot, but each one of them is pretty short. It's to the point that if you really focus, then you can do each problem like approximately 1 minute, at most 2 minutes. Okay, so it will take you around 1 hour to do this section, homework from this section. Okay, now let me give you introduction to what you will see on Thursday. On Thursday, we will dive in further into sequence and summation notation, which is series. Okay, 9.2 is on what we call arithmetic sequence and series. And series. A sequence is arithmetic if it has common difference. Okay, arithmetic sequence have this pattern. The first term to the second term to the second term to the third term to the fourth term and on. You keep on adding the same number. So the second term is the first term plus a difference, common difference d. Then another difference, and then another difference. So you can think of this way, like the second term is the first term plus d. The third term is the second term plus another d, like that. Such that we have a general pattern. The nth term is the first term plus n minus 1 times d. That's arithmetic sequence. Now, from function point of view, arithmetic sequence mimics or very similar linear function. Mimics linear function. Now, the first example of in this sequence that I gave you was 3, 7, 11, 15, 19, and on. Do you remember that? Okay, now where the nth term is actually 4n minus 1. Now, when I say it mimics linear function, try to correlate that with fx equals to 4x minus 1. Okay, where the difference in the sequence is equal to the slope in the linear function. Okay, I hope by identifying that way, it is easier for you. Okay, the nth term of an arithmetic sequence is this. But Thomas, what you write there seems to be different from what you write here. Actually, if you play around, this is dn minus d. So you see dn plus a sub 1 minus d. That's what we have there. The d is 4. Okay. And a sub 1 minus d is negative 1. Okay. Basically, eventually you will see a linear function type, linear sequence, to be more precise, arithmetic sequence. Okay. Now, S sub n is the sum of the first n terms. We also call that the nth partial sum. S sub n basically means S sub n, the nth partial sum basically means a sub 1 plus a sub 2 plus a sub 3 all the way to a sub n. So nth partial sum, if we write that using summation notation, is the sum of the first n terms. I think I want to use k here, but k from 1 to n. Now, if the sequence is arithmetic, then the n partial sum equals to the number of terms divided by 2, the first term plus the last term. Now, that's another formula I need you to memorize for arithmetic sequence. This way, then, on Thursday, we can do it really fast. We have only 2 sections left for your test 4, 9.2 and 9.3 for your test 4. Now, on Tuesday next week, I will give you new material. It will not be in your test 4, but it will be in your final. Okay, now on Thursday, we will learn 9.2 and 9.3. Now, 9.2, you need to memorize these 2 formulas. This formula here and this formula here. In 9.3, you will have 3 formulas to remember. Okay, but let me end here. See you then on Thursday.